In our previous sessions, we have discussed about relational operators, arithmetic operators, and we have discussed about arithmetic, relational, and I think we have discussed bitwise also. Yeah, bitwise and equality operators. We have directly started with the coding of these operators. So I told to try the test bench for this bitwise operators, right? So if you have tried, it's okay. I will also write the test bench for bitwise operators, and let me see the output. Yeah, up to here, up to equality operators, we have seen the outputs. So let me display the results for bitwise operators also. So for bitwise, and I will display first. So the value of bit underscore and is percentage b comma uh, not instantiated. First of all, let me instantiate it where bit underscore and bit underscore or where bit underscore or, and I have bit underscore nor and bit underscore xor. Bit underscore and or nor and xor, and let me display this. So my initial inputs are 001 and 100. Three tick binary 001 and 100. So bit underscore and is percentage b comma bit underscore and I'll display this bit underscore or is bit underscore or, and I'll copy this and paste it over here. I have bit underscore nor also, so display it here nor bit underscore nor and bit underscore xor. So for the inputs 001 and 100, I am performing these operations. Let me copy this display statements and paste it over here. And for the input 01x and wait a minute, I will change the input now, x1x. These are my inputs, so I will perform bitwise and or nor and xor. So now let's see the outputs what we are getting. So let me run the simulation. Wait a minute, it will take a minute. Yeah. So at the console we can observe whenever input is 0001 and 0100, the bitwise and is 0 and bitwise or is 1, bitwise nor is 1. We are performing bitwise operation. So let me take uh, the output as 4 bit so that it will be more precise. Output bitwise and or not and XOR. So I'm taking 4 bit so that it will be more clear, the results will be more clear, and I will change in test bench also. So bitwise 4 bit. Yeah, so let me relaunch it. Mm. So when my input is 00001 and 0100, then bitwise and is all zeros. It will here it is performing bitwise and between these two inputs. One and with 0 is 0, 0 and with 0 is 0, so on. And bitwise or, it is like a normal or operation between each individual bits. So 1 or with 0 is 1, 0 or with 0 is 0, like that. And coming to bitwise nor, we know the NOR operation, right? It is basically complement of uh, OR operation. So 1 OR with 0 is 0. Wait a minute. Sorry. 1 OR with 1 NOR with 0 is 1, and 0 or NOR with 0 is equal to 1. Like this, we will get it. And coming to XOR, we are getting this. And coming to this unknown values 001x and xx1x, here we can see the bitwise AND operation. So the AND operation between unknown and unknown will be an unknown, and whereas a number and unknown will be equal to 0. Since 0 and with any number will be equal to 0, but 1 and with any unknown will be an unknown. So here remember this 0 unknown, 0 bitwise and with any unknown value is 0. Wait a minute. So 0 so remember this 0 NAND with 0 and with any unknown value is 0, whereas 1 and with any unknown value is unknown. So remember this difference. And in case of OR, uh, here we can see x OR with x is an unknown, and coming to 1 OR with 1 is equal to 1, and 0 or with unknown is obviously it's 0. And coming to NOR operation, here we can see unknown will result in unknown, and 1 NOR with 1 is 0. Sorry, previously I was um, showing this OR. So coming to NOR, unknown, NOR with unknown will be an unknown, and 1 NOR with 1 will be equal to 0, and any other 0 with unknown NOR with unknown will be equal to unknown only. So remember this. So these are some important points to remember. So is this clear for everyone? Can we move forward? Is this clear, right? So remember these points I'm mentioning here. And also we have 0 XOR with unknown is 0 XOR with unknown is the same number. That is it, we will get unknown only. In place of unknown, if we have 1 XOR with 0, then the output will be 1. And yeah, these are some of the points to remember. So up to here, is it clear, right? So moving on, we have reduction operators. Yeah. So coming to reduction operators, we have and we have and operator. This is not bitwise and, these are reduction operators. I will show you. And we have NAND, and we have OR and NOR and so on. I will write it here, make as outputs. So output reduction operator output is only 1 bit. So I will make it reduction underscore and output reduction underscore OR, and I have output reduction underscore NAND and output reduction underscore NOR and reduction output reduction underscore XOR, and I also have output reduction underscore XNOR. So these are some of the reduction operators. So let us see one by one. So I will assign reduction underscore and is equal to, so if I want to use reduction operator and operator, then the symbol is equal to ampersand, and I will perform reduction and on A. So this is a reduction and, so and of A. If you see the output, then it will be more clear what's happening here. First of all, let us use all of them. Reduction underscore or will be equal to oblique A. Sorry, yeah, and assign reduction underscore XOR will be equal to, I'm performing all the operators on E only. So, and I have assign and what are all operators I have used. Wait a minute, XNOR also, yeah. So assign reduction underscore XNOR is equal to not of cap A. So yeah, these are the reduction operators. Let's see what we are getting here. Yeah, so let us include them in the test bench. Y reduction underscore and reduction underscore or reduction underscore XOR XNOR and yeah, and or XOR XNOR. I will instantiate them also. So reduction underscore and reduction underscore or underscore XOR underscore XNOR. So let us quickly display them also. Yeah. So reduction underscore and or XOR XNOR. Here it will be reduction underscore and or XOR and XNOR. Yeah, let me copy this quickly and paste it in the second scenario. Let me relaunch it. Wait a minute. Sorry. Here it should be comma. Yeah. So let us see in the console what we are getting. Wait a minute. Should be reduction underscore or and reduction underscore XNOR underscore XNOR and reduction underscore, sorry. So at the output we can see reduction underscore and is equal to 0. Wait a minute. This is our first case. So I'm performing AND operation on A, that is 0001. So reduction underscore AND is 0. Since it will perform AND on each individual bits of the number. So it will perform AND on this number, that is 0 AND with 0 is 0, and it will perform 0 AND with 0 is 0, and 0 AND with 0 is 0. So output will be 0, and or will be equal to 1. Reduction underscore or will be equal to 1, since it will perform or operation between the individual bits of the input. And uh, why I'm getting reduction underscore XOR is equal to high impedance. Let me check it. Okay, so I have used NAND and NOR, but I have not instantiated them in the test bench. So it is taking the value of NAND and NOR in place of XOR and XNOR. So that's why I was getting that high impedance. Now let us resimulate it again and check it. Yeah. So the console, we can see reduction underscore XOR will be equal to 1, since 0 XOR with 0 is equal to 0, 0 XOR with 0 is equal to 0, 0 XOR with 1 is equal to 1. So the output will be equal to 1, and XNOR, it is reverse. 0 XOR with 0 1, 1 XOR with 0 is 0, 0 XOR with 1 is 0. So XNOR will be equal to 0 in the first case. Whereas in the second case, for the input 001X, I am performing all the reduction operators. So reduction underscore and is 0, since 0 and with 0 is equal to 0, 0 and with 1 is equal to 0, and 0 and with unknown is equal to 0, since we have discussed that 0 and with any number is equal to 0. And coming to 0, reduction underscore or 0 or with 0 is equal to 0, or with 1 is equal to 1, and 1 or with any number is equal to 1. We have discussed it. And coming to XOR, up to here we will get some value, and XOR with an unknown is equal to an unknown, and for XNOR is also same. So these are the reduction operators in Verilog. So this is clear, right? Can we move forward? So We have shift operators also. Let's discuss it quickly. Output shift left underscore shift, and we have output right underscore shift. So there are actually arithmetic and logical shift. We will discuss it afterwards. For now, we will discuss logical shifting only. So I want assign left underscore shift. Then the syntax is a left shift by. So if we want left shift by 2 bits, then we can mention 2. So a will be left shifted by 2 bits, and assign right underscore shift is equal to, I want b to be right shifted by 3 bits. So this is a syntax for left shifting and right shifting. Let us quickly add it in TB also. It will be while left underscore shift and right underscore shift, and we will add it here. So left underscore shift and right underscore shift, and we'll display it here. Left underscore shift of a, and we are left shifting, and here right underscore shift is right shift of b. Let me quickly copy this. And paste it over here. So I'm left shifting a by 1 bit and right shifting b by 2 bits. So let me recompare it. Wait a minute. I missed a comma. So my first input is 0001. So I'm left shifting it. Wait a minute. Sorry. I should take 4 bit so that we can analyze it. And in TB also will change it quickly. So yeah, my first input is 01, sorry, 0001. So left shift of 0001 is 0100. I hope left shift operation is clear, right? So I'm not explaining it in detail. We will discuss it in digital. So the left shift of 0001 is 0100, and the right shift of 0100 by 2 bits is 000. We are getting 000. So this will be right shifted. So one will be driven out. And coming to my second input, that is 001x, left shift operation. The result is 1x00, and double x 1x. I'm right shifting it by 2 bits, so it will be equal to 000x. So observe here what's happening. While right shifting, zeros are getting appended. Here we can see, instead of x, when we are right shifting it, zeros are getting appended, and for left shifting also zeros are getting appended. So this is the concept of left shift and right shifting in Verilog. So is this clear, right? If you have any doubt, you can ask me.